We learnt earlier that transition elements have this characteristic property of having variable oxidation state, which results from the fact that they can always lose the two 4s electrons to form a 2+ ion, but then potentially an oxidizing agent could come along and take additional electrons away from the 3D subshell to create ions with higher charges. So because of that, there is lots of scope for redox reactions in which the transition element switches between different oxidation states. So you need, first of all, to be able to apply the skills that you already have in relation to redox reactions of constructing half equations, combining those together to make overall equations for redox reactions, and also using electrode potentials to predict whether particular oxidations will be feasible or not. So here's just a couple of examples of that, based on the fact that iron typically exists as either Fe2+ or Fe3+ in aqueous solution, and you can switch between them by using particular oxidizing or reducing agents. So here are examples of going in both directions. So if we start with Fe2+, you can see that the electrode potential for Fe2+ being oxidized to Fe3+ is plus 0.77. So in order to go from Fe2+ to Fe3+, you need an oxidizing agent which has an electrode potential that's more positive than that, okay, which is what manganate does. So looking at those electrode potentials, the manganate Mn2+1 is more positive, so that can go in the reduction direction. Remember, positive goes with reduction, so the more positive electrode potential, that can go in the reduction direction, where manganate gains electrons to form Mn2+. And of course that means the Fe2+ can be oxidized to Fe3+. And that is a very common titration. It's one of those manganate 7 titrations that you often get questions about. But you can see now in terms of electrode potentials why that's a feasible process. On the other hand, if you want to go from Fe3+ back to Fe2+, you need a reducing agent. So you can see that that can be achieved using iodide, because if you compare these two electrode potentials, you get a less positive one for iodide and iodine. So less positive means that can go in the oxidation direction. So I- can be oxidized to iodine, losing 2 electrons, and therefore the more positive one is the Fe3+ Fe2+1, so that can go in the reduction direction, which means iron 3+ can be reduced to iron 2+. So there are lots of examples that they can choose to illustrate that feasibility of redox chemistry that you already know how to do. But there are also some specific redox reactions that you need to know. Now the syllabus explicitly says that you're not expected to memorize equations for these reactions. I guess you might have to work them out in certain situations, but don't spend time memorizing the equations. You just need to know the particular reagents that can cause these oxidations or reductions to occur and learn the color changes that accompany them. So again, it's just a lot of memory work, I'm afraid, but there's not a lot to understand here. It's just knowing that these things can happen. So the case we've already talked about is iron 2+ and iron 3+, and those specific reagents we used in the examples are the ones you need to know. So if you want to oxidize Fe2+ to Fe3+, you need to know that you can do that using aqueous acidic potassium manganate 7, so MnO4- and acid. On the other hand, if you want to go in the other direction and reduce iron 3+ to iron 2+, you need to know that iodide can do that, and that in that case aqueous iodine is formed. So the solution that you get at the end has Fe2+, which is pale green, but the colour is dominated by the iodine in that case. So although you've formed this pale green ion, the colour you see is the brown of the aqueous iodine. In the case of chromium, you need to know about the oxidation of chromium 3 plus to chromium 6 plus. Remember, it's not a Cr6 plus ion, it's a complex, it's an ion with oxygens in there, which is chromate. And you can bring about that oxidation from 3 plus to plus 6 chromate, CrO4 2 minus, using hydrogen peroxide in alkaline conditions. So again, you just need to learn that that's the case, and that the colour change you get is from that violet or green chromium 3 plus colour to yellow chromate. Chromate is closely related to dichromate because they both have a plus 6 oxidation state, and it's just a pH dependent equilibrium, which you can see down here. So this isn't a redox reaction because the chromium is plus 6 in both cases. It's just a transformation that, as you can see, is going to depend on the H plus concentration, because if you increase the H plus concentration, it will shift to the right and form dichromate. If you decrease the H plus concentration, it can shift back to the left and form chromate. So it is different from dichromate, but they're both the same oxidation state. Of course, you can also go in the opposite direction and reduce dichromate to chromium 3 plus, and you're used to that happening when you oxidize alcohols or aldehydes with dichromate. But you also need to know that you can use an inorganic reducing agent, and zinc metal is the one that they expect you to know. Okay, so that's the chromium case. With copper, the two common oxidation states of ions are copper 1 plus and copper 2 plus. And you need to know that copper 2 plus can be reduced to copper 1 plus by adding iodide. And in that case, again, what you end up with is a sort of rather complicated mixture, because copper 1 iodide is formed, which is actually a solid. So instead of getting an aqueous copper 1 ion, you get copper 1 in the form of a white solid. But again, in the reaction, the iodide is oxidized to iodine, so you get this white solid which will fall out of the solution, but the solution itself is brown due to the iodine. So you need to know that that's how you can reduce copper 2 to copper 1. And copper 1 ions, in fact, don't exist as stable hexaqua ions. If you get copper 1 into aqueous solution, it immediately disproportionates. So aqueous copper 1 just isn't stable, and half of it will get oxidized to copper 2, half of it will get reduced to copper metal. So that can happen if you start with copper 1 oxide. So that's this compound, Cu2O, which is a red coloured solid. And like all oxides, it will react with acid. Oxide plus acid goes to salt plus water. But of course, that salt will contain aqueous copper 1 ions, and they will immediately disproportionate. So what you actually get is this reaction, where the copper 1 oxide reacts with acid, and instead of getting 2 aqueous copper 1 ions, you get some copper metal, which is a pink metallic solid, and you get copper 2 plus, so the solution turns blue. Okay, so again, quite a lot of memory work to be done there in learning these redox reactions. Those are the only specific ones that you need to memorize. You also need to be aware that this property of transition metal ions, that they often act as catalysts, in many reactions that results from their ability to switch between different oxidation states. You don't have to learn any specific cases where that's the mechanism of oxidation, but they sometimes will ask questions where, for example, you get to use redox potentials to try and work out a catalytic mechanism. So this is an example of where that takes place. So this is just using manganate 7, which you're familiar with as an oxidizing agent, getting reduced to Mn2+, and in this case oxidizing ethane dioate ions to carbon dioxide. And if you do that experimentally, it behaves very strangely, because at the beginning it seems to be really slow, and in fact you often have to heat it up to get a reasonable rate of reaction. But you find that as soon as it gets going, it gets faster and faster. And the reason is that the manganese 2+ ions that are formed as a product also act as a catalyst for the reaction. So once you've formed a few of them, they will catalyze the reaction and make it go faster. And that's called autocatalysis. So the way that works is this, that initially there's no manganese 2+ there to act as a catalyst, and therefore the rate is very slow. But as soon as you get some Mn2+ present, you can get this two-stage reaction taking place, where initially what the manganate 7 does is not oxidize ethane dioate directly, but oxidize Mn2+ to Mn3+. So having formed a bit of Mn2+, the manganate can then oxidize it to form a little bit of Mn3+ in this first reaction. And then the Mn3+ will in turn react with the ethane dioate and oxidize it and revert to being Mn2+. So overall, the Mn2+ is being a catalyst, because it's used up in the first reaction and regenerated in the second one. Now, you don't need to learn that story, but it's worth just making sure you understand what's going on there, because, as I say, they do occasionally get you to kind of try and work out catalytic mechanisms like that. And you can see why this would work, because the problem with the overall reaction with MnO4- with its negative charge trying to oxidize ethane dioate with its negative charge is that the two negative ions will tend to repel each other, and that will slow them down as they approach one another. So the probability of a successful collision is limited by the fact that they're slowed down by the repulsion between them, and therefore they're not very likely to hit each other hard enough for the reaction to happen. But if you go via the catalytic mechanism, you have a negative ion hitting a positive ion in the first step. So manganate has to collide with Mn2+, and because they're attracted together, that's going to accelerate them as they approach, and so they will actually be more likely to hit each other hard enough, and that makes a successful collision more likely. And then the same is true in the second step, because now you have the positive Mn3+ and the negative ethane dioate. So that's the way that catalysis works. So as I say, don't attempt to memorize that. That's not something you're supposed to learn, but it's just illustrating how a transition element can act as a catalyst. So be aware that that ability to switch oxidation states is typically the key to that. Okay, so that's it for the redox chemistry, and that basically takes you to the end of the stuff that you need to know about transition elements. So you can now do the remainder of those questions.